Processing a series of items with iterators. The iterator pattern allows you to perform some task on a sequence of items in turn. An iterator is responsible for the logic of iterating over each item and determining when the sequence is finished. When you use iterators, you don't have to re-implement that logic yourself. In Rust, iterators are lazy, meaning they have no effect until you call methods that consume the iterator to use it up. For example, the code in listing 1313 creates an iterator over the items in the vector v1 by calling the iter method defined on vect. This code by itself doesn't do anything useful. Let v1 equal vecbang123. Let v1 iter equal v1.iter. Once we've created an iterator, we can use it in a variety of ways. In listing 3.5 in Chapter 3, we used iterators with for loops to execute some code on each item, although we glossed over what the call to iter did until now. The example in listing 1314 separates the creation of the iterator from the use of the iterator in the for loop. The iterator is stored in the v1 iter variable, and no iteration takes place at that time. When the for loop is called using the iterator in v1 iter, each element in the iterator is used in one iteration of the loop, which prints out each value. For val in v1 iter, println got val. In languages that don't have iterators provided by their standard libraries, you would likely write this same functionality by starting a variable at index 0, using that variable to index into the vector to get a value, and incrementing the variable in a loop until it reached the total number of items in the vector. Iterators handle all that logic for you, cutting down on repetitive code you could potentially mess up. Iterators give you more flexibility to use the same logic with many different kinds of sequences, not just data structures you can index into, like vectors. Let's examine how iterators do that. The iterator trait and the next method. All iterators implement a trait named iterator that is defined in the standard library. The definition of the trait looks like this. Pub trait iterator, type item, function next, mutable reference to self, return, option, self item, and then methods with default implementations elided. Notice this definition uses some new syntax, type item and self item, which are defining an associated type with this trait. We'll talk about associated types in depth in Chapter 19. For now, all you need to know is that this code says implementing the iterator trait requires that you also define an item type. And this item type is used in the return type of the next method. In other words, the item type will be the type returned from the iterator. The iterator trait only requires implementors. The iterator trait only requires implementers to define one method, the next method, which returns one item of the iterator at a time wrapped in sum, and when iteration is over, returns none. We can call the next method on iterators directly. Listing 1315 demonstrates what values are returned from repeated calls to next on the iterator created from the vector. Test attribute function iterator demonstration. Let v1 equal vecbang123. Let mute v1 iter equal v1.iter. Assert equals v1 iter.next and some reference to 1, then some reference to 2, some reference to 3, finally none. Note that we needed to make v1 iter mutable. Calling the next method on an iterator changes the internal state that the iterator uses to keep track of where it is in the sequence. In other words, this code consumes or uses up the iterator. each call to next eats up an item from the iterator. We don't need to make v1 iter mutable when we didn't need to make v1 iter mutable when we used a for loop, because the loop took ownership of v1 iter and made it mutable behind the scenes. Also note that the values we get from the calls to next are immutable references to the values in the vector. The iter method produces an iterator over immutable references. If we want to create an iterator that takes ownership of v1 and returns owned values, we can call into_iter instead of iter. Similarly, if we want to iterate over mutable references, we can call itermute instead of iter. Methods that consume the iterator. The iterator trait has a number of different methods with default implementations provided by the standard library. You can find out about these methods by looking in the standard library API documentation for the iterator trait. Some of these methods call the next method in their definition, which is why you're required to implement the next method when implementing the iterator trait. Methods that call next are called consuming adapters, because calling them uses up the iterator. One example is the sum method, which takes ownership of the iterator and iterates through the items by repeatedly calling next, thus consuming the iterator. As it iterates through, it adds each item to a running total and returns the total when iteration is complete. Listing 1316 has a test illustrating the use of the sum method. Function iterator sum, v1 equals vecbang123, let v1 iter equal v1.iter, let total of type i32 equal v1 iter.sum, assert equals total and 6. We aren't allowed to use v1 iter after the call to sum, because sum takes ownership of the iterator we call it on. Methods that produce other iterators. Other methods defined on the iterator trait, known as Iterator Adapters, allow you to change iterators into different kinds of iterators. You can chain multiple calls to Iterator Adapters to perform complex actions in a readable way. But because all iterators are lazy, you have to call one of the consuming adapter methods to get results from calls to Iterator Adapters. Listing 1317 shows an example of calling the Iterator Adapter method map, which takes a closure to call on each item to produce a new iterator. The closure here creates a new iterator in which each item from the vector has been incremented by 1. But this code produces a warning. So let v1 of type vec of i32 equal vecbang123 v1.iter.map and then closure of x plus 1. The warning we get is this: warning, unused standard iter map, which must be used. Iterator adapters are lazy and do nothing unless consumed. The code in listing 1317 doesn't do anything. The closure we've specified never gets called. The warning reminds us why. Iterator adapters are lazy, and we need to consume the iterator here. To fix this and consume the iterator, we'll use the collect method, which we used in chapter 12 with inv_args in listing 12.1. This method consumes the iterator and collects the resulting values into a collection data type. In listing 1318, we collect the results of iterating over the iterator that's returned from the call to map into a vector. This vector will end up containing each item from the original vector incremented by 1. Let v1 of type vec of i32 equal vecbang123. Let v2 of type vec of underscores equal v1.iter.map close x plus 1 dot collect. Assert equals v2 and vecbang234. Because map takes a closure, we can specify any operation we want to perform on each item. This is a great example of how closures let you customize some behavior while reusing the iteration behavior that the iterator trait provides. Using closures that capture their environment. Now that we've introduced iterators, we can demonstrate a common use of closures that capture their environment by using the filter iterator adapter. The filter method on an iterator takes a closure that takes each item from the iterator and returns a Boolean. If the closure returns true, the value will be included in the iterator produced by a filter. If the closure returns false, the value will not be included in the resulting iterator. In listing 1319, we use filter with a closure that captures the shoe size variable from its environment to iterate over a collection of shoe struct instances. It will return only shoes that are the specified size. Attribute for shoe derive partial eq and debug. Struct shoe has two fields, size, type u32, and style, type string. Function shoes in my size takes shoes, which is a vec of shoe, and shoe size, which is a u32, and it returns a vec of shoe. Shoes.intoIter dot filter close s dot size equals shoe size dot collect. Attribute test function filters by size. Let shoes equal vecbang shoe with fields size 10, style, string from sneaker, shoe size 13, style, string from sandal, and shoe size 10, style, string from boot. Let in my size equal shoes in my size, taking shoes and 10. Assert equals in my size and vecbang shoe with field size 10, style, string from sneaker, shoe size 10, style, string from boot. The shoes in my size function takes ownership of a vector of shoes and a shoe size as parameters. It returns a vector containing only shoes of the specified size. In the body of shoes in my size, we call intoIter to create an iterator that takes ownership of the vector. Then we call filter to adapt that iterator into a new iterator that only contains elements for which the closure returns true. The closure captures the shoe size parameter from the environment and compares the value with each shoe's size, keeping only shoes of the size specified. Finally, calling collect gathers the values returned by the adapted iterator into a vector that's returned by the function. The test shows that when we call shoes in my size, we get back only shoes that have the same size as the value we specified. Creating our own iterators with the iterator trait. We've shown that you can create an iterator by calling iter, intoIter, or itermute on a vector. You can create iterators from other collection types in the standard library, such as hashmap. You can also create iterators that do anything you want by implementing the iterator trait on your own types. As previously mentioned, the only method you're required to provide a definition for is the next method. Once you've done that, you can use all other methods that have default implementations provided by the iterator trait. To demonstrate, let's create an iterator that will only ever count from 1 to 5. First, we'll create a struct to hold some values. Then we'll make this struct into an iterator by implementing the iterator trait and using the values in that implementation. Listing 1320 has the definition of the counter struct and an associated new function to create instances of counter. Struct counter, one field, count of type U32. Implement counter, function new returns a counter. Counter with one field, count is 0. The counter struct has one field named count. This field holds a U32 value that will keep track of where we are in the process of iterating from 1 to 5. The count field is private because we want the implementation of counter to manage its value. The new function enforces the behavior of always starting new instances with a value of 0 in the count field. Next, we'll implement the iterator trait for our counter type by defining the body of the next method to specify what we want to happen when this iterator is used, as shown in listing 1321. Impl iterator for counter. Type item equals U32. Function next, mutable reference to self, returns an option self item. Self.count plus equal 1. If self.count is less than 6, sum self.count, else none. We set the associated item type for our iterator to U32, meaning the iterator will return U32 values. Again, don't worry about associated types yet. We'll cover them in Chapter 19. We want our iterator to add 1 to the current state, so we initialized count to 0, so it would return 1 first. If the value of count is less than 6, next we'll return the current value wrapped in sum, but if count is 6 or higher, our iterator will return none. Using our counter iterator's next method. Once we've implemented the iterator trait, we have an iterator. Listing 1322 shows a test demonstrating that we can use the iterator functionality of our counter struct by calling the next method on it directly, just as we did with the iterator created from a vector in listing 1315. Test attribute. Function calling next directly. Let mute counter equal counter new. Assert equals counter.next and sum1, then sum2, sum3, sum4, sum5, and then none. This test creates a new counter instance in the counter variable and then calls next repeatedly, verifying that we have implemented the behavior we want this iterator to have, returning the values from 1 to 5. Using other iterator trait methods. We implemented the iterator trait by defining the next method, so we can now use any iterator trait method's default implementations as defined in the standard library because they all use the next method's functionality. For example, if for some reason we wanted to take the values produced by an instance of counter, pair them with values produced by another counter instance, after skipping the first value, let me try that again. For example, if for some reason we wanted to take the values produced by an instance of counter, pair them with values produced by another counter instance after skipping the first value, multiply each pair together, keep only those results that are divisible by 3, and add all the resulting values together, we could do that, as shown in the test in listing 1323. Test attribute function using other iterator trait methods. Let sum of type U32 equal counter new dot zip, taking counter new dot skip 1 dot map close A and B, A times B, dot filter close X, X remainder 3 equals 0 dot sum, assert equals 18 and sum. Note that zip produces only 4 pairs. The theoretical 5th pair, 5 and none, is never produced because zip returns none when either of its input iterators returns none. All of these method calls are possible because we specified how the next method works, and the standard library provides default implementations for other methods that call next.